Okay, so I hope you're getting used to it by now, but 3.1 is a definition, and the definition of boiling point. It is the temperature at which the vapor pressure of the liquid is equal to the atmospheric pressure. Do not say equilibrium, do not say point. It is the temperature at which the vapor pressure of a substance or a liquid equals atmospheric pressure. So you guys get it wrong because you say point. It's not a coordinate, it's a temperature. The boiling point is a temperature in degrees Celsius normally. And it's not at equilibrium with anything else. It is equal. So please, very, very common definition. So please just know it. Which one of the following is A, B, or C is mainly a liquid at 100 degrees Celsius? So this is always a little bit tricky, but there are three numbers here, and they're asking you about 100. They want one answer. Choose the one answer that is on the one side of the number they're asking about. So 46 and 78 are both below it. Choose the 118. If you need more of an explanation, this thing changed to a gas and the boiling point of 46 degrees. This thing changed to a gas at 78 degrees, and this thing is going to change to a gas at 118. And we are currently sitting at 100. So the first two have already gone. C is the one that hasn't changed to a gas yet. But when they ask that type of question, which one of the 4 or 3 or 5, you typically answer the one that's on the one side of the number. So A and B are both below 100. Answer the one that's higher than 100, because there's only one number that does that. Then for number 3.3, explain the difference in the boiling points between A and B. So A and B are both 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. But the brackets in B mean that it actually looks like this. And I don't know, again, whether you know, but it's got one of those. So A is a straight chain with a Cl, and B has a branch. And so you need to argue not strength, but size or surface area. So explain the difference. You need to mention that they both have the same intermolecular forces. Both of them have the same intermolecular forces, but A has a longer straight chain. So how I would like us to do it is when we're comparing A and B, we say that both of them have dipole-dipole intermolecular forces. So again, this is like the recipe question. So if I can just do a quickie recipe question, it's you name all of the intermolecular forces. And then you compare either the strength, which is not relevant in this case, or the surface area, which is related to the size. So this argument is a surface area argument. So because it's got a larger surface area, the intermolecular forces are stronger. They're not stronger on their own. They're exactly the same. And so hydrogen bonding and dipole-dipole. Hydrogen bonding is stronger. Therefore, you need more energy. For the size argument, it's the surface area of A is bigger because it's less branched, or the surface area of B is smaller because it's more branched. So the surface area thing is a branching thing. So you talk about the surface area. So if it's less branched, that means it's got a larger surface area and the intermolecular forces are stronger, therefore it's more energy, therefore a higher boiling point. Or a higher lower vapor pressure, or a higher melting point, or a higher viscosity. So everything is directly. Stronger is higher, except for the vapor pressure, which is the opposite. So if we can just look here what they're looking for, longer chain length, that's the size thing, and then stronger or more intermolecular forces. You see here, they have this here. Please don't ever say that. I don't even want to mention it, but van der Waals forces used to be accepted, and it's not accepted anymore unless it gets to a point where, 200,000 kids have sent van der Waals. because some of the textbooks still say it and some of the schools don't know that they've changed it. It's not really changed. Sorry, I mean, no one cares about this. But basically, van der Waals is not so much wrong as non-specific. So if you say van der Waals forces, you're talking about sport. Van der Waals forces includes hydrogen bonding, dipole-dipole, induced dipole, London. It includes all of those. So it's like you're saying that Keegan is the best at sport, rather than saying Keegan is the best at rugby. So if saying van der Waals forces, I need you to be more specific. I need you to tell me which type. Dipole-dipole, London, hydrogen bonding. So as usual, so they're talking about here the size, the strength, the energy. That's how it goes. That's how these types of questions go. That's the recipe question. So now, sorry, if we can just go to the next one, which is basically the same thing. So for 3.4.1, which I don't have in there, I think I have it down here something. Oh goodness, have I lost 3.4.1? I think it's here. No, oh goodness. Okay, so here's 3.4.1. Which one of these values represents X, the boiling point of compound D? So once again, we've actually got the same kind of situation. D is an aldehyde, and C is an alcohol. Alcohols and acids have hydrogen bonding, which is the strongest type of intermolecular force that we deal with. Aldehyde is dipole-dipole, which means that aldehyde must have a smaller boiling point, a lower boiling point than the alcohol. It must be lower. This number is the only number that's lower. So 75 degrees Celsius, I can show you here that's the answer, must be the answer to the boiling point for compound D. And they say fully explain your answer in 3.4.1. So now once again, it's going to be the strength of the intermolecular forces. So C has stronger intermolecular forces than D. So they say you must fully explain. So ideally, again, I would like you to say that C has hydrogen bonding and D has dipole-dipole. Hydrogen bonding is stronger than dipole-dipole, so more energy is needed to overcome the intermolecular forces in C. So there we go. Oh, they say break as well. Break is not correct. You should say overcome. But again, they get quite lenient because of the language and everything else. But there's also like a million variations of the answer to that. We don't need to look at those. Then, for the very last one, the atmospheric pressure is now changed to 83 kPa. So here it says that the atmospheric pressure is 101. It is now changed to 83. Basically, when things boil, the vapor pressure is the pressure of the substance. So if this one was 80 and this one was 50, and the atmospheric pressure was 101.3, you would have to heat this one up and heat this one up to reach 101.3 pressure. If you increase the temperature, you increase the pressure. You should know that if you've ever driven for hours and hours and days and miles in a car, the pressure in the tires increases if the heat of the tire increases. So if a substance has a higher vapor pressure, it is closer to the goal and it has a lower boiling point. That is just a loose explanation of what happens with vapor pressure and boiling point. This one has a lower vapor pressure, which means it has a higher boiling point. I need to heat this one more to get the 50 to 101.3. That was just a recap. Sorry, I didn't really need to tell you that. But basically what they've done now is they have changed this to 83. They have decreased the atmospheric pressure. They have basically lowered the goal. What would happen to the boiling points? They would decrease. Because in order for me to go from 80 to 101, I would need, and again, random number, 10 temperature. Now that I only need to go to 83, I need less than 10 temperature. The boiling point would be lower. The English on that was delicious, but anyway, let's see if I can find this memo. Come on, Terry. Where's the memo? There it is. There it is. See there? Decreases. Sorry. Decreases.